Hello, everyone, and welcome again to class. This is Mrs. Thompson, and today we will be looking at polar coordinates and polar equations. Our objectives are as follows: plotting points using polar coordinates, converting a point from polar coordinates to rectangular coordinates, converting a point from rectangular coordinates to polar coordinates, converting an equation from rectangular form to polar form, and converting an equation from polar form to rectangular form. While covering these topics, we will also incorporate some graphing. Starting with plotting points using polar coordinates. Please pause this PowerPoint and watch the video entitled Plotting Points Using Polar Coordinates. You may find this video in this week's Moodle tab in the resource area. So it's in the same location that you found this particular PowerPoint. After watching this video, please return to this PowerPoint presentation. Well, hopefully you paused and watched the video. It brings a deeper understanding to what we are covering on this slide. Relationships used when converting a point from polar coordinates to rectangular coordinates. The x value of your point in our rectangular coordinate system is equal to r times the cosine of the angle in our polar coordinate system. And likewise, the y value of your point in the rectangular coordinate system is equal to r times the sine of the angle in our polar system.
Yeah.
The graph shows the angle, commonly referred to as theta, that contains the point. Again, this is a typical point on the x and y axis in our rectangular system, but as you can see, identifying or labeling this point using polar coordinates, the second value, theta, is the angle whose terminal side the point lies on, and the first value of the point is r. And of course, in a little bit, we'll have a formula for r, a reminder of that formula. Well, converting a point from from polar coordinates to rectangular coordinates. We are given the point with an r value of 6 and an angle of pi by 6. So to convert to rectangular coordinates, we use the formulas and substitute. So to find the x value of our point, we plug in for r. R is 6. Our angle is pi by 6. So 6 times the cosine of pi by 6, which from chapter 5, you know is the square root of 3 over 2. When we multiply, we end up with 3 times the square root of 3 for the x value of this point. Finding the y value using the formula y equals r sine theta. R again is 6, angle pi by 6. The sine of pi by 6 is 1/2. Half of 6 is 3, so the y value is 3. So the point with polar coordinates 6 pi by 6 has rectangular coordinates of the square root, 3 times the square root of 3 for x and 3 for y. Here is an additional example. If you would like to pause the video for this additional example and study it, please feel free to do so. Moving forward with converting rectangular coordinates to polar coordinates, and we will start with points lying along an axis, so a point on an axis. Determine the polar coordinates for the given rectangular coordinates. And the point that is given to us has an x value of negative 4 and 5/10 and a y value of 0. So the point is plotted here in green at an x value of negative 4.5 on the x-axis. So the distance from the origin to the point, the distance from the origin to the point is 4.5 units. So the radius is 4.5. The point lies along the negative portion of the x-axis, so theta equals pi. Therefore, the polar coordinates are the r value of 4.5 and the angle that provides the point in this location, which is pi. Converting a point from rectangular coordinates to polar coordinates. So we are continuing with converting from rectangular coordinates to polar coordinates, but now we will be experiencing a point that is not on an axis. The point that we will be converting is the point to -2. Well, the first piece that must be found is the value of r. So, just as in previous chapters, the formula for r is r equals the square root of x squared plus y squared. We have the x value and the y value given to us in our point. So we simply plug those in and use the order operation. Squaring, adding, and finally taking the square root of the sum, which gives us a square root of 8. That must be simplified. 8 is 4 times 2. Square root of 4 is 2. And of course, leaving us with root 2. So we have our r value. That is the first value in our polar coordinate system for this point. We still have to find the second value. Please note, however, that the point 2, -2 is in the fourth quadrant. That is an important fact. Moving forward to complete finding the second portion of this point in our polar coordinate system. In other words, finding the value of theta. Well, the tangent of theta, or the tangent of the reference angle for theta, is equal to y over x, and yes, you must take the absolute value of that quotient. So plugging in for y, our point in our rectangular coordinate system has a y value of -2, also plugging in for x, that value of 2. We divide, we get 1 after taking the absolute value. Now we need to find the inverse tangent. Well, the angle with a tangent of 1 is pi by 4. We are almost there with finding the value of theta. But this is our reference angle. This little substrip or r stands for reference, because we know that our angle was in quadrant 4. Pi by 4 is just a reference angle because it's in quadrant 1. So we need an angle in quadrant 4 that has the same tangent as pi by 4. So of course, to find that angle, we take 2 pi, a complete circle, and subtract pi by 4, placing us in quadrant 4. 2 pi minus pi by 4, or minus 1/4 pi, equals 1 3/4 pi. We normally write these as improper fractions, so final answer of 7/4 pi. If you want to evaluate 7/4 times pi in your calculator, you get an approximate answer of 5.5. So, in polar form, the coordinates of this point is 2 times the square root of 2 and 5.5 or 5.50. Want 2 places behind the decimal. If you need more examples on converting a point from rectangular coordinates to polar coordinates, watch the video Converting a Point from Rectangular to Polar Coordinates, posted in Moodle in the resource section for this week. At this point, we will be moving to converting equations from rectangular to polar form and then in the opposite direction. Example, convert the equation in rectangular form to polar form. The given equation is x equal 9. Very direct. This is a very direct problem. We know that x is equal to r times cosine theta in our polar system, so we make that substitution. The equation is in polar form, but the problem is not complete because we must get it in the proper form, which means anytime an equation is in polar form, please remember to always solve for r. So solving this equation for r, we find that r equals 9 over cosine theta. Looking at an additional example of converting from rectangular to polar form. In rectangular form, our equation is 3x minus y equals 12. Substituting with x is equal to in our polar system, r cosine theta, and likewise making that substitution for y, r sine theta. Now, solving for r, the variable that you're solving for can only appear once. To make r appear once, since we do not have like terms, we have to use a technique from Math 171, and that is to factor out r as a GCF. After doing so, r can be isolated by performing the opposite operation, so r equals 12 over 3 cosine theta minus sine theta. This next example is very similar, but we are going in the opposite direction, from polar form to rectangular form. So r cosine theta is replaced with x, and r sine theta is replaced with what is equal to, which is y, and the problem is complete. If you want to write the equation, since it results in the equation of a line in slope-intercept form, that is fine. Solve for y. Either form is okay.